In our last lecture we were discussing about the floor planning problem. If you recall, we had looked at some of the representation of the floor plan. We had looked at some of the methods of floor planning, like the one which uses integer linear programming, like the one which uses the concept of the rectangular dual graph, and lastly we looked at a method which was some kind of a hierarchical approach. Starting from smaller floor plans, we merged the blocks together into bigger blocks, and then systematically we got the complete floor plan. And finally, we were talking about another approach which is based on simulated annealing based technique. There we had mentioned that the approach is based on a very unique representation of the solution, namely for a given floor plan you have the slicing tree topology, assuming that it is a sliceable floor plan, and you take the Polish postfix equivalent representation of the tree, and that Polish expression will be your representation of the solution. So, basically the simulated annealing formulation is based on that Polish postfix expression. So, just to recall once more, simulated annealing based technique must talk about the solution representation, which I have just mentioned. Here they use the Polish postfix notation corresponding to the slicing tree. Of course, moves will have to be defined which will change a particular solution into another, and finally a way to evaluate the cost. Fine. So, now let us straight away come into some of the details of the algorithm. Now, the solution representation I have already mentioned, it is a postfix notation of the sliceable floor plan tree, slicing tree topology. And regarding the other parameters, first let us define the various moves that we can have or define for going from one particular solution to another. Well, in terms of the Polish postfix notation, there are three different moves which are defined. See, a particular Polish notation may look like this: A, B, say vertical partition, C horizontal partition, D vertical partition. Suppose this is an example postfix notation. So, the first one says that you swap any two adjacent operands. Well, in terms of the expression, you take any two operands, say A B or B C or C D, and simply swap them. So, here for example, if you swap B and C, it will become A C vertical B. Okay. So, the first one simply exchanges two operands. Second one, it works on a so called chain. Now, a chain is defined, for example, I take any two operands. For instance, I take the operand B and the operand D. So, whatever lies in between, that is called the chain. Okay. So, the second kind of the move says that for a chain, which means for a given pair of operands, say B and D, you complement the operators, like this bar will become dash, this dash will become bar. So, if it is a vertical operator, it will become a horizontal one, horizontal will become vertical. So, complement a series of operators between two operands. And third one, it says swap two adjacent operators and operands, which means say your expression was A B bar C dash D bar. Suppose I select these two, C and this bar. So, this will be transformed into dash C D bar. But one thing you understand, the third one, it is not necessarily true that any time you apply this, this will become a valid expression. So, every time you apply C, you will have to check for the validity of the resultant expression, because for example, this is not a valid expression, because on the left there are too few operands, right. Well, another thing, we talked about something called normalized postfix expression. Normalized expression, if you recall what we said, normalized postfix. So, here the requirement was that there should not be no two adjacent vertical or no two adjacent horizontal, and in this scheme all the solutions are constrained to be corresponding to normalized postfix expression, because we had seen that if you have an unnormalized postfix expression, suppose you have a postfix expression say E1, E1 is unnormalized, okay. Corresponding to that expression you will be having a floor plan, this will be a floor plan. Now, for most of the floor plan I have mentioned that it is possible to find another Polish postfix expression say E2 which is normalized. So, for the same possible floor plan you can have another alternate representation which is a normalized one. So, if we constrain ourselves only to normalized expressions, it does not really harm, means the advantage gain is that we can restrict the search space. So, this searching for a solution will be faster. Okay. Now, looking at the definition of this normalized expression, if you just look at these moves once more, if we swap two adjacent operands, so a normalized expression remains normalized, right. Similarly, if you complement a series of operators, means some of the dash you make bar and some of the bar you make dash, that will also leave it normalized, because it is always enclosed within two operands, fine. But there is a possibility that the third one may convert the expression into an unnormalized one. Like of course, in this example you cannot have, but in general you can have. So, in the third case, so for the first two cases you need not do anything. If you choose to make move A or move B, you can do it blindly, but for move C you will have to first check the validity of the Polish postfix expression, whether it is well formed or not, and number 2 you will also have to check whether it is normalized or not. So, only if both the conditions are satisfied, then only you can accept move C as a valid move. Okay. Fine. So, these are the moves which are defined, and regarding the cost function, they had selected a very simple cost function. You take a measure of area and the interconnection length. Now, area, the way you estimate is that, well, you are finally placing the blocks on the surface of the floor. So, you are trying to have a floor plan. Suppose block A is being placed here, block B is being placed here, block C is being placed of the smallest enclosing rectangle of the area of the floor plan. Say suppose D is again here. So, A is the area of the smallest rectangle which envelops the given basic rectangles, and L is the overall interconnection length. We had earlier said that you can have a very coarse measure of interconnection length in, so means when you are at the floor planning level. So, here for every pair of blocks say Bi and Bj, the way you would proceed is that there can be several interconnection lines. So, you take the centroid of this rectangle, take the center of this rectangle, take the center of this rectangle, and you assume that all these interconnecting, you can say pins, they are residing at the center, and you just measure the center to center Manhattan distance, just multiply it by the number of lines that goes, that gives a measure of the length. So, you do it for every pair of blocks I and j, and that will give you an estimate of the overall interconnection length. And of course, W and W2 are some parameters which users can specify, whether you are more interested to minimize the area or the length, or equally you want to give weightage to both. So, W and W2 can be anything. Okay. Fine. So, this was how the simulated annealing algorithm was framed. Of course, the initial temperature, number of iterations, those are fixed out through experimentation. But I am giving an example to show that these moves A, B, C which we had just mentioned, these really help in moving from a bad solution towards a good solution. Of course, in this example I am not illustrating the simulated annealing algorithm, but I am illustrating the 3 moves, how they can make a solution improve. Okay. Suppose this is my initial solution, this is an initial floor plan, suppose this is 3, this whole one is 3, okay, this. So, this 1, 2 are separated by a vertical slice, this and 4 are separated by a horizontal slice, and this entire thing and 3 are separated by a vertical slice. So, this is the resultant floor plan. Now, suppose I say in simulated algorithm at each step you will have to randomly select which move you want to make, A, B or C. Now, once you choose to select one of the moves, then you will have to randomly select the pairs of operands and operators where you want to make the move on. So, there are actually 2 steps of it. First you select the move number, then you select the 2 points of the solution where you want to make the move. Like for example, in the first step when you make move A, say you choose to swap these operands 4 and 3. Okay. So, the modified solution becomes this, where 3 comes here and 4 comes here. In terms of the floor plan, you see now means the position of 3 and 4 gets exchanged. Now, assuming although this this diagram you cannot see the exact dimensions on a relative scale, suppose 4 was bigger than 3. So, maybe 4 will be filling up this space more fully than 3, 3 will come here. Next move B, move B means maybe because simulated annealing is a randomized algorithm, you can always go from a good solution to worse solution. So, whether you accept it or not, that depends on that probability again.
That will be an unaccepted solution because that is not worst, that can't be done.
Yeah, sure. There are some solutions which are not feasible, you can check those things here. Fine. From here, if you want to make move B, you have to define a chain again. Well, here the way the chain is defined is that, say you define the chain between 2 and 3, these 2 operands. Well, in fact, incidentally within these 2 operands there is a single operator, you change it to horizontal. So, now this says that 1, 2 and 3 all will be separated by horizontal slices, and this entire thing and 4 will be separated by a vertical slice, something like this. And finally, if you make move C on this, say you swap these 2 operands and operator make it 4 dash. Now, instantly this becomes a feasible solution, and what happens, this 1, 2 will be together with the horizontal slice, 3 and 4 will be again together with horizontal slice, these 2 will be together with a vertical slice. So, maybe you will be fitting them very nicely like this. So, just to show you that these moves can make a solution improve. Yes.
So, while moving for optimizing the area, do we also at each step consider the interconnections, or we consider interconnections later?
See, at each step we look at the cost function. Cost function takes care of area as well as interconnection. Yes.
So, does move B?
Move B. Move B says, if you recall, move B says that you identify a chain, a series of operators between 2 operands, they are complemented. So, in this case you have chose to select these 2 operators 2 and 3. So, here in this example there is one operand only. So, that one operand you exchange, you must swap, you complement it in fact. The vertical you make horizontal. So, it becomes this.
Sir,
yes.
First of all, we need to have a graph according to which we will floor plan, because depending upon the interconnects, like
Yes.
but here suppose Earlier 1 was not connected to 3 at all directly, but here it is 1 and 3, the edges are touching.
See, here you mean?
Yes, sir.
See, in this example, just for illustration, we are only looking at the area gets minimized, but interconnection will also come into play. So, if there is a strong interconnection between 1 and 3, then in terms of the cost function, a good solution will require 1 and 3 to be together. So, just this for the sake of illustration, but once you implement, you will have to take care of everything, and the final solution which you will be getting, that will take care of the cost function you are defining. Okay, it will try to find out a solution which is good in that respect. Okay. So, we had looked at a number of solutions for floor planning, and I had mentioned that most people what they do now is that either they do floor planning or placement together, or they use some kind of a hierarchical approach. Well, this simultaneous handling approach has also been reported by it, but I really do not know whether anyone uses this in any commercial tool, but in placement they do use it, and simultaneous handling is the most important, you can say, the algorithm used in placement. Okay. But in case of floor planning, I do not think simultaneous handling is used in any commercial tool, but this is an interesting scheme or approach, you can say. Yes.
The expression changes to 1 to horizontal 3.
Yes, after move B it becomes this. Yes.
Is it normalized?
See, this is not, but if the expression was 1 2 3 dash dash 4 bar, this was unnormalized, because these two dashes were consecutive, but here there is an operand separating them. This is normalized, but this is not. But actually these two are equivalent, you see, both means the same thing. Okay. So, we had looked at the different algorithms for floor planning. Now, there is another step to be done either during floor planning or immediately after that. This is called pin assignment. Well, apparently pin assignment is a much simpler subproblem as compared to floor planning, but we will see this is also important, because a good pin assignment can give you a very good layout finally. So, first let us try to understand what pin assignment means, what is the problem all about. Okay. So, in pin assignment, the basic problem or purpose is to define the signal that each pin will receive. So, what does this mean? You think of a block. Well, to the external world, this block is nothing but a rectangular area structure with some pins on its periphery, right. There is some circuit inside, there is a netlist inside. Now, which of the signal lines will be connected to which pin? That is essentially the pin assignment problem, because if the block is fixed and pre-designed, you do not have a choice, it is already done. But in case of flexible blocks or wherever you can make this change, you can possibly, for example, this input to this gate you can assign either to this pin or to this pin. It depends on the interconnection with the other blocks. You try to reduce the routing complexity or the congestion. So, that with that in mind, you try to have a good pin assignment. You are trying to define or you are trying to assign a signal to the individual pins of a block. This is the pin assignment problem. Okay. Now, this can be done during floor planning or even during placement. See, after placement is fixed, you can also do that. We will see how, because after placement is, for what I had said earlier, that in floor planning we are making a tentative placement of the blocks on the floor plan, but after the sizes or the dimensions of the box have been finalized, the locations of the pins have been fixed, and also the areas, the routing areas between them have been finalized, that we say that we have got a placement. Like what I mean to say is that I am taking a very simple example. Suppose we have a floor plan like this. this is a sliceable floor plan. Suppose there are 5 modules. This is a floor plan. Now, if we have a refinement whereby we get something like this, this we call a placement. Now, in a placement the exact pins have been defined, the netlist has been defined, you also know that which pin you have to connect to which other pin of the other block, and the routing or the interconnection areas are also defined, which are the places which are available for interconnection. Okay. So, this is the difference between placement and routing. Now, here what we say that even after placement is complete, still there is some scope for pin assignment, we will see how. Okay. So, we are seeing that the scope for pin assignment does not end even after placement is complete, even after placement there is some scope for pin assignment, fine. So, if the block is flexible, not yet designed, then a good assignment of pins will give you a better placement obviously. So, interconnection to the other blocks will be more easy to do. But if the block is already designed, you do not have a choice of reassigning signals to the pins, still you can do some exchange of the pins, we will see how, to improve the routability. Some pins of an already designed block can still be exchanged.
So, a design block means the placement has been done.
Placement has been done, or the block you are taking from a library for example, where the internal circuit is known and which signal goes to which pin, that is also known. But still you can make some manipulation in terms of assigning signals to the pins, we will see how. Okay. Just to look at the problem once more. So, for pin assignment we have the tentative location of the blocks, it can be during floor planning, it can be during placement. So, you know how many pins are there on each block. For fixed block you know the exact locations, for flexible block you know that well this pin will be having, this block will be having 5 pins. Now, the exact location of the pins may not be known, but maybe you will specify a ordering that your pin signal A will be first, then B, then C, then D, then E, but the exact location you can fix up, that whether it will be here or here, but the ordering can be specified by the user, and of course netlist, how these blocks are interconnected. So, requirement is to find the exact pin locations, or to talk about in slightly more general term, to assign the signals to the nets. Objective is to minimize the net length. Minimize net length, as a byproduct you will also reduce the congestion in routing. Okay. Now, I have said that if your blocks are already designed and the locations of the pins are already fixed, still there is some scope for exchanging some signals with respect to the pins. How? Well, the concept is very simple. You can define functional equivalent or equipotential pins. These are two different concepts. Functional equivalent pins are two distinct signals, but if you exchange them, it does not change the functionality of the circuit, like the two inputs of an AND gate. So, if one is A and one is B, it does not matter if you call this A and call this B. So, if the function which is realized by this block is commutative, then you can do this. A B and B A are the same. They are said to be functional equivalent pins. They are not equipotential. Equipotential pins are C and D. They belong to the same net. So, the pins or the signals which belong to the same net, they are called equipotential, but signals whose exchange does not alter the functionality of the circuit, they are called functional equivalent, right. Now, let us see how does this matter in terms of you can say final placement or routing. Well, I am taking a very simple example. Suppose we talk about gate array designs. Now, in a typical gate array, the chip will consist of a large array of say simple gates, NAND gates, 2 input NAND gates. So, in terms of the area, in terms of the layout for example, so a particular cell for a gate may look like this. These reds indicate polysilicon lines. Well, I am showing the power supply lines by black, and in the middle you have say, well, the transistor laid out. So, let us say this is the diffusion layer, there is a connection with VDD, this is VDD and this is ground, there is another connection here, and there are some transistors which will be the pull ups and pull downs. So, there will be a pull up transistor here which will be connected like this, and there will be 2 pull downs, thin ones. They will be connected to, one will be connected to this, other will be connected to this. Okay, so, I am not showing the exact layout, and this will be connected to this somehow. So, with respect to this particular gate array, well, if you look at it functionally as a small rectangular box, you will be having 3 pins on top and 3 pins on bottom. These will be the 2 inputs, say A and B, and the output F. These are also available from top. So, if you have the requirement of connecting some pin of here to some other pin of this, say the output of this you want to connect to the input say here, maybe there is another gate similar like this. So, the output of that you want to connect to say the input this. So, obviously, here is a crossing, but if you swap these 2 pins, then you can get another solution where there is no swapping. So, it becomes like this. This output will come to the first pin, this output will come to the second pin. So, where the routability is improved, the congestion is less. So, the idea of this equipotential and the functional equivalent pins and their utilization in case of routing and congestion control is like this. Okay. So, what we have just said is essentially the optimization of the assignment of nets within a functional equivalent or equipotential pin group. So, just the example I have cited is something like this, similar to this. So, there are 2 outputs whose 2 blocks signals are coming like this, but if you reassign them, if there are equipotential or functional equivalent, then you can swap them. So, they become like this. So, this reduces congestion. Congestion means your routing will be easier now, right. Okay. Now, let us look at some of the design style specific issues for pin assignment. Well, for full custom you have entire flexibility. There will be many blocks which may be flexible, which are not already pre-designed. So, you have the flexibility of assigning pins on the periphery. So, full custom design style exposes the complete, you can say, the range of the things you can do during pin assignment. But here normally you do it in 2 different steps. Number 1 is that during floor planning you can change the pin location along the block boundary, because the blocks may be flexible. So, the block may finally assume a shape which is a square, or it can be like this, or in some cases it can also be L shaped. In general you can also have blocks like this. So, once you finalize the shape of the block, the pin location along the boundary of the block will get defined. They can be changed during this step with an eye towards congestion control. Like the example I have cited, the interconnection with the other block should be easy, number of signal crossing should be minimized, something like that. And secondly, during placement you make utilization of the other concept like functional equivalent or means or the equipotential pins in order to assign the nets to the actual pins. So, this can be done in two distinct steps, because if you try to just do both these things together, you may lead to a little problem. The problem can become a little complex. And standard cell or gate array, here the problem is simpler. See, here basically you will have to identify the functionally equivalent pins, and the net assignment you can do some swapping out there. So, you have the flexibility of permuting the assignment of the nets for the pins which are functionally equivalent, just whether you will be connecting like this or will be connecting like this. Changing equipotential pins, this is another flexibility. So, for the standard cell you do not have any flexibility of changing the position of the pins, just for the equipotential or the functional equivalent pins you can play around with it. Similar is the case for gate array, right. Okay, so here I will not go into the details of this algorithm, so I will give you an idea what these algorithms are all about, how do they work roughly. Broadly speaking, the generalized pin assignment problem can be solved in several techniques. Some of these methods are concentric circle mapping, topological and 9 zone method. But for very specific sub problem, particularly in case of standard cell based design, you can have something called channel pin assignment, where you have the concept of routing channel and you are doing pin assignment with respect to a particular routing channel. Okay. Fine. Let us try to see these methods. Well, the method of concentric circle mapping is simple in concept. This method uses or virtually assumes that there are two concentric circles. The objective is to planarize the interconnection, means they try to remove the crossings. In interconnections, if you just imagine it as a graph, planarize means they can be laid out on a plane without edges crossing. So, it tries to planarize the interconnections as far as possible. So, how? See, there is a block with pins on its sides. Well, you are wanting to interconnect these pins to pins of other blocks. So, pins on the block being considered, this one, are shown as points of the inner circle. I will show you an example. There is a concept of an inner circle. Similarly, the points to which you want to make the connections for the other blocks, those are shown as points on another circle, that is called the outer circle. So, we will see through the example that the problem is tackled or handled in two different paths. First is that with respect to these two circles, you assign the pins of the inner block as well as to the other pins to which you want to connect to some points on the circumference of these two circles. Number 2, you map a point on this circle to a point on the other circle, somehow like this you map them. So, these are the two steps of the method. First, you assign the pins to points on the circumference of the circles, then you try to find out a correspondence between the two circles. Okay. So, this is whatever I have said is very conceptual. Let us take an example to understand what I mean. Okay. This is an example problem where this is the block B with 6 pins on the boundary. These are the points which may be points of the other blocks I am not showing, but these pins have to be connected to these 6 points outside. Okay. First thing is that you define 2 imaginary circles. The first circle will be just inside the inner pins like this. The second circle will be just inside the outside points. This was the nearest point, so you define a circle like this. The third step is you take the center of the circle and draw straight lines to all the points of the inner and the outer circles. So, the straight lines to the inner points corresponding to the pins of block B will be intersecting the inner circle into these 6 points. Similarly, the lines for the outer points will intersect the outer circle in these 6 points. So, now you get some points on the inner circle and some points on the outer circle. Now, these are 2 possibilities. Now, what they try to do? They try to rotate the inner circle. This is the worst case scenario, this is the best case scenario. Suppose this is the order in which you want to connect the lines, but if you rotate the inner block, then the interconnection will become a little skewed. So, you just have means this method has an estimate to find out what is the length of the nets if you rotate, means what is the orientation of the block, that will give you the best interconnection solution. And in this step also, if there is some concept of equipotential or functional equivalent pins, you can swap them to reduce crossing. So, all these concepts are taken into account in this method. So, actually I am not going into the details of the implementation of the algorithm, but this is the concept.
So it may happen that one pin in the inner circle is mapped to more than one pin in the outer circle.
Yes, possible. Okay. So, this method is conceptually simple, and this method tries to make a good assignment of the pins, so that during the routing the nets do not cross too much. Okay. The second modification to this concentric circle mapping is something called topological pin assignment. See, topological pin assignment is similar. So, see, in case of concentric circle mapping, you are assuming that there are no obstructions in between. When you are trying to interconnect, you are finding the shortest distance. But topological pin assignment assumes that there can be some obstructions or interference from other components which can act as barriers. So, you will have to go around the barriers for interconnections. So, the idea is like this. Suppose you have 3 blocks, and this method also takes care of nets which can connect more than one point. Suppose there is a net like this which must connect 3 points. Okay. Now, the way this method progresses is that you identify one of these 3 blocks as the primary block. Let us say this one you define as the primary block, and this point you assume to be at the center of the primary block. Like you see what it says, if a net has been assigned to more than 2 pins, then the pin closest to the center of the primary component is chosen. Okay. This is the primary block and this is the pin closest to it. There can be another pin also. For example, there can be a pin out here also which also gets connected to the same net. So, in that case, among these two, which one is the closest, you take this. This is chosen as the center of this. Now, from there a method similar to concentric circle mapping is used. So, again you try to see with respect to this net, well, this method works with one net at a time, not with all nets. So, you do some kind of a concentric circle mapping, you try to do reassignment and find out that how you can configure, or if there is flexibility of moving the pins. So, exactly where should the pin be placed, so that the distance with the other pins is minimized, or something like that is used. I am not going to detail. So, the pins are assigned to the nets in a particular order. You say once you have this imaginary circle, there can be 1 or 2 pins on the periphery, there will be some other pins outside which you want to connect to it. So, there will be an outer circle also. So, you try to find out an orientation, which means that exactly where on this surface this pin has to be located. You can see, or you can say that if this pin is moved slightly out here and this pin is moved slightly out here, then the total cost gets reduced. There will be a measure of the cost. You try to find out the relative position of the pins on this circle, which will finally get mapped back into some pin on the boundary. Okay. So, you will say that the pin will be here and the pin will be here. So, this topology mapping and concentric circle mapping is similar, with the difference that concentric circle takes all nets at a time, but this takes one net at a time, and this can handle multi-terminal nets.
So
yes.
the cost is in the term of number of crossings?
Cost is in terms of the total length and the number of net crosses, both are taken into account. Right. Okay. And there is another approach which was proposed. This is based on the concept of zones. This is called a 9-zone method. It is like this. Say you have a block, this is a block to which some other blocks will have to be connected. You define 9 zones like this, 1, 2, 3, 4, 5, 6, 7, 8, 9 is itself. So, 8 externally, 9 is itself. These are the 9 zones. Now, what we do is that for each net, okay, center of the coordinate system is here. This is the center of the coordinate system. This component is called the pin class. Well, the central block which you are choosing this block is called the pin class. Now, the concept is like this. Now, you take one net at a time. Suppose for this particular block, you see that there is one net which has to go out from this pin, it has to connect this pin and this pin. So, you imagine a rectangular region which will be enclosing this net. Now, you try to move around this point, so that the area of this rectangle, imaginary rectangle, is minimized, and then you try to map it to one of these zones, which zone this imaginary rectangle belongs to. So, essentially what you try, each net you try to map to one of these zones, and your objective will be to map the different nets to different zones, so that congestion is distributed means uniformly across the zones. So, this is an indirect method, not directly. Here the individual nets you assume to be in zones. You can move around pins to change the areas of the rectangles. Your objective will be to map a rectangle to one of the zones, and you will try and see that more than one net do not fall into the same zone.
So in the first algorithm, we just change the orientation of the blocks. We are
Yes.
not changing the relative positions of the pin.
See, I am saying orientation of the block, but if the pins are flexible, you can as well keep the block fixed and change the pins. That means the same.
The pins were not changing. Like,
Huh?
if two pins were A and there were 2 pins 1 and 2,
Huh.
they were still together. Like, but in this we are moving them. They are choosing one pin at a time, sir.
Yes, we are choosing one pin at a time.
So the distance between the pins are changing. So is that mean that we are going for full?
Yeah, here this method we are assuming we are going for full custom design. The pin definitions are not yet fixed. Yeah, internally we can make those changes, because if that ordering is fixed, then means you cannot just do much with this playing around, because once one of the rectangle is fixed, the other gets means constrained severely. You are right.
What was the image you said, like first you minimize the area, then you map it to different zones. But they might be.
Now minimize area is one thing. That means another thing is also you will have to see that the rectangle falls into one of the zones, because here everything is mapped into zones.
Yeah, like they are conflicting requirements.
Conflicting requirements, absolutely. Some of you can say some of the rectangle may span 2 zones. Yes.
So, please explain this one also.
Here I am saying, suppose we have a pin out here. This pin wants to make a connection to an external pin here, an external pin here, and an external pin here, say. So, with these points you try to find out an imaginary bounding rectangle. Say the imaginary bounding rectangle will be like this. Now, you see that this imaginary bounding rectangle spans zones 1 and 5. Then you see that if I move around this pin, can I put this into one of the zones? But in fact, in this example you cannot. So, this net has to be mapped or assigned to 2 zones 1 and 5. But if there is a flexibility, then you can move this around and try to map it into one of the zones. Suppose this point was not there and this pin was initially here, then the rectangle would have been like this big. Now, if you move this point up, then it will span only zone 1, like that. Okay, fine. So, among the specialized method, I told you that if you are having a standard cell based design, you can have you can simpler sub problem, which is called channel pin assignment. Now, a channel is something like this. So, we will look into channel in much more detail later when you talk about routing, but a channel is something like this. There is a block, say Bi, there is a block Bj, there is a rectangular region between the blocks Bi and Bj, and the pins are located above on the surface of Bi on the periphery and below. The objective is to connect some of these pins to some of these pins. This is the channel routing problem. So, there are pins on the 2 sides of the channel, there is a given net list, you will have to interconnect them using minimum number of tracks. Okay. Fine. So, for channel route pin assignment, the problem is that in modern day VLSI design, most of the designs are based on standard cell based ones. So, we have channels or existence of channels are there in most of the designs. So, understanding that channels are a very important part or important, you can say important proportion of the routing we have to do. So, it will help if you try to do some pin assignment in the channels, which will be reducing congestion and the routing areas. Like in fact, there are a number of heuristics which are used. Here I am showing only one. Like for example, suppose in a standard cell based design, you have 2 rows of cells. Okay, these are the pre-assigned cells on top and bottom. Say I am giving a specific example. Suppose these 2 pins are here and there is one pin here and one pin here. Now, your objective will be to connect this with this and this pin with this pin. Now, in order to do that, you can see that you will be requiring, well, these interconnections are normally done in 2 different layers. This will be in one layer, this will be in some other layer, this will be in the other layer. Similarly, for this interconnection, this will be in one layer, this will be in another layer, this. So, for this simple sub problem, you see that you are requiring 2 channels or 2 tracks. since the two nets are crossing and the span of the two nets overlap, you cannot do with one track. There is a section where both the nets are overlapping, you have to have two different tracks for them. But suppose I do something like this, well, in a standard cell design, although I place the blocks one after the other, I can slightly shift one block to the left or right. So I can, so what I can do is that, say I will be doing something like this, like say I will be aligning any one of the nets so that one pin is getting just above the other pin. So maybe I will be shifting, just I am taking the same example, say I will be shifting this pin slightly to the right. So maybe I will be having some blank space here, or if this blank space come, I may be putting some other cell here if I can. So I will be shifting this cell slightly to the right. Okay. So now I will be having a situation where these two pins will be coming one just exactly on top of the other. Say this pin will be here, maybe just exactly below it I will be having this pin. The other pin will be moving further right, this pin will be here. So now the advantage again is that for this net, since they are vertically exactly one above the other, I can route them in the same layer, and this one I can route in only one track. Okay. So I can reduce the number of tracks required for routing if I have a scenario like this. So in cases where I have flexibility, I can use even equipotential or functional equivalent pin to swap pins and try that if this can be done, or even I can shift some blocks around, or I can swap some blocks also. So in standard cell based design you have this flexibility, so that this kind of you can say some relative pin assignments are done. But one thing, in this channel pin assignment, this is normally done at the time of channel routing itself. It is not that you are first doing pin assignment, then you are going for routing. It is really difficult to do it separately. So here, although we are saying that this kind of a thing can be done, this will reduce channel congestion, everything is fine, but this cannot be done in a step which is much before the routing. This has to be done along with the routing itself. Okay. So we have talked about some algorithms related to floor planning and pin assignments, and we will see that subsequently we have some other steps also called, first of course is the placement, then we will have to go for routing. But we will see that in many situations we may have to go for an integrated approach. This again depends on the design style. For example, in the standard cell approach I told you that this pin assignment and routing can go together. Okay. So in an integrated approach, once you understand the different design stages much better, you can go for an integrated approach. Like for example, floor planning and placement are often merged together nowadays. They are not two distinct different steps, they go hand in hand. Similarly, for some design styles, placement and routing can also be combined together. So actually while placing, you also do some processing on routing, so that your interconnection interconnection effort later gets reduced. Of course, some estimate is already done during placement. See, during placement you have to evaluate something, some kind of a cost function, so that your routing complexity is less. But since you are already spending some time, if you can spend a little more time so that some of the routes also gets established, then it helps in the later routing steps. Okay. So this integrated approach is something which is possibly the best approach, but there are a number of unsolved problems. Still this is a problem of research. Okay. So actually people are still working on these integrated kind of approaches.
So before this integrated approach came into play, was it a practice to go back and change it again? I mean, after routing you find that something could be done in placement, so go back.
See, even integrated approach, whatever, even in the most modern CAD tools available today, there often you will have to go back and make some changes. You will see after laying out, you will see that your power requirements, some of the area parts of the chips will be becoming very hot, that is consuming power performance, that part is consuming lot of power. So, you will have to reorganize the floor plan again. Some of the modules maybe you have to take up to the cooler portion of the chip, and then you will have to again redo a part of it. So, this kind of iterative thing will be there. So, for a very big design you cannot expect that everything will be done automatically and everything will be fine. So, you will have to iterate. Okay, so thank you.